Yeah, so I will start talking or giving some examples of operation from both airborne and UAV. I have just gathered some videos where we fly the system similar to the Veneer installation and for UAV. Then I have afterwards video I made yesterday about boresighting some data that was acquired last week in Svalbard. And then at the end also a video about doing the direct georeferencing of that data after the boresight is done. So I will just start. The first one is a LinkedIn video. No, first I have for the hardware. Yeah. Just as a reminder, right? It's a which I described yesterday, the hardware setup in an aircraft where you have typically a Veneer and a sphere camera. You have a computer. So by the way, UAV, the UAV system is exactly the same, but everything is inside the UAV payload, so everything is smaller, of course. But you have the DAU, you have a touch screen where you have an interface, you are starting and stopping acquisition, adjusting the integration time, which I talked about yesterday also, which is extremely important to adjust it correctly or to a level where you have the max signal noise ratio in your data. You have a navigation system here with a GPS antenna. And you have the most important for syncing is this event pulse that is timed here on the navigation system. So let's start with first overview of what we have been doing in HySpecs, and then some more specialized videos. An airborne installation. This is one we did in Germany, I think in 2010, I believe. every time you change the integration time, you see it's dark, the button on top, you cannot press any buttons. That's because it's taking a new dark current before you can start an acquisition. So you have a mechanical shutter inside that closes and then takes the dark current. That was a Beechcraft, and this is just for the INS logging as well. I'll start it. This is in Turkey in 2015. This is an FMS, and I'm planning a post track where he sees he's now trying to align with the flight line, the straight line you see here. And he has this line-up point that Agnar talked about yesterday as well. And he's telling me, I can see the aircraft now is trying here to align this line. Have to have an FMS to fly, right? Then some pilots use just the Garmin GPS. Here is mounted on a stabilized platform. It's the Sumag GSM 1000. Yeah, good. So it's yeah, stabilizing, roll pitch and heading while you fly. This is a Cessna 402, I think. Demonstration for a customer that purchased the week after, but so the screen is just on my lap, it's not mounted. Typically, of course, this would be mounted somewhere. So you have the Veneer Preview here. So this is the Veneer Preview, the Veneer 1800 and the Spirit 384 here. Red pixels here. So you have this quality control pixels on the side here telling you if you are under or if you have okay dynamic range or not. And you have the red pixels which are telling you that it's saturating, right? But it's important, as I mentioned yesterday as well, to increase the exposure time until the scene of interest is close to saturation. So for you, you don't care, like if you're looking for vegetation here now, right? You don't care if the roofs are on is saturating. So that's okay, right? You can still use the data. So that's important. That's also important if you plan to do stuff with reflectance targets. I know many people are used to using spectral lens 99%. It's usually not a very good idea because you need to reduce the integration time or exposure time for the target not to saturate, so that actually your SNR in the images will be worse just because of this. So we typically use 40 or 50% instead of 99%. So this is telling in real time, right? What is the current accuracy of your INS solution, the real-time solution? So you can see here first the data, latitude, longitude, height, roll pitch, heading. You can see the standard deviation. So you have 35 centimeters, 46, 60 centimeters in height. This is the real time, right? So this is not been post-processed. And but you can see the degrees here on the roll, pitch, and heading is not too bad in real-time solution, 0.014. And same here, heading is always worse. So this is quite similar, or it's actually better than the APX15 that is on the drone system. And you get the status here. And the most important also is to see that you are getting events, right? When you are acquiring an image, the events should go up, right? So that you see that everything is connected. Okay. Let's go to UAV. I will not look at, we will not see this whole video, but I will jump to some locations. So just first, we're going to show, this is we did a live demo at the Stratus that was at Rochester University, our Institute of Technology in the US. We had a 60-minute live demo, which apparently was 45 minutes. I thought it was 60 and it was 45, so we almost made the whole thing in 45 minutes. So we are starting with flying, copying data, then starting the processing. So I can show you this how fast it actually is to do the processing. This is not something that has to take months after you're done with your acquisition.
It's a live demo of the Hyperspecs VS620. We are flying today on a BFD drone. We are in Norway, so it's 8 o'clock in the evening and the sun is about to go down. So we just have to move quickly to do a flight so we get some data with some sun. So let's move over to the drone system. Yeah, so it's an octocopter with the Gremsy H16 gimbal with the VS620 here. We have a 5.8 gigahertz data link that's communicating with the ground station, and we will be connecting to the computer inside during the flight. Yeah, are you ready, Nils? Yes. Yeah. You ready from the drone, please? Take off. Okay, auto mode. So go into auto mode. So you can watch here the flight plan in the DCS flight planning software. You can see the drone is moving here. So what it's going to do first, it's going to do a quick alignment of the navigation system, so you get good INS accuracies. And then we're going to fly 3 parallel flight lines, which we're going to process afterwards. And then it will end, stop with also an alignment before we land.
This is like I mentioned yesterday. This is to get the INS solution good very fast.
With the remote desktop to the mission computer inside the system, where we adjust the exposure times, the frame period, relative to the speed, where you have data from the INS, and then we start and stop the acquisition. We can do just a test acquisition now in the beginning. It's a bit dark, so I'll put the gain up on the preview here. It's actually saturated. I put it in high gain mode. So I will turn it down a bit. The sun just.
The short-wave camera has a high gain and low gain mode, so you can adjust the full well, right?
I will adjust down the exposure time to maybe Let's try 15 milliseconds. Now it's there's a mechanical stripper inside. Now it's closing, taking a fresh dark current for this exposure time. And when it's green again now, it's ready to start an acquisition. Here you can also see the temperatures of the FPA on the Veneer camera and on the sphere camera. You ready? Now we will see a waterfall preview. This is just 3 selected bands from the 490 channels of the camera, which is showed here, the raw data showed during the flight. And you can see the red part here is actually bands going into saturation. I have the sphere camera now in high gain mode since it's so dark or so late. Over to the DCS again. About to be finished.
This here is just a normal flight, a Boresight flight we do actually for, or this is actually not a Boresight flight, but we do this Boresight flight for every system we deliver. So every week we are at this shooting range flying new systems that we are
Now the first
delivering.
flight time is done. We are about to go into the second one. You can see here that the alignment of the IMU is aligned. You can see here the standard deviations of the solution that we have now, and also I'm ready. Also the number of events here, which is basically time tagging every frame in the Hyperspectral image. You can also have a real-time view of the link status and the battery voltage for the payload this side. Now you can see it's a lot darker. The sun disappeared. With the top of the tree, and it's long shadows. Can increase the
And this as well here you have auto acquisition, so you can connect the UGCS flight planning software. It's on the other computer.
We're about to finish the second flight line.
Can trigger the start and stop automatically. So
it actually has an auto acquisition input, so we can trigger start and stop automatically. We are flying with not the newest chassis.
I will let myself talk in the video, I think.
The FPA inside here is cooled to 175 Kelvin for the sphere camera, and the Veneer is cooled to ambient temperature around 25 or stabilized. So when we're done here now, we will land, and then we will copy over the data. Also here, the new chassis has an external bay. Here we will do a copy with a USB 3 SSD drive. It will just take a few seconds, but yeah. And then we will go into I'm ready. Go in and process the data. The ambition here is to do the real-time processing. Real time or within 45 minutes. Yeah. Now we are basically done with the 3 flight lines, and if we go here again, it will also finish now with an alignment, also done automatically before we land. So we want to have the navigation system at the best possible performance. The Applanix APX15 inside can have an accuracy on roll-on pitch on 0.025 degrees, which is about 1.2 pixels in our system. And the GPS in post-processing mode, if you use 2 IMUs, can be around 2 to 3 centimeters, while today we only use a single IMU for the payload, So it will be around 9 to 10 centimeters accuracy. Then we'll end the session here and exit the software and wait for the drone to land so we can copy the data.
Lars.
This gimbal of this payload now, or platform, weighs 25 kilos. It can fly for 20 minutes. The payload itself is about 6 kilos without the gimbal, and with the gimbal, it's about 8 to 9 kilos.
Can you remind us again which sensor that is?
So now I'm copying over the data, the Planix data, and I will just turn off this on here. And I'm copying over the Hyperspectral data. As I mentioned earlier, the chassis has an external bay. You can just take out the hard disk, but now we just copied over to an external hard drive instead. Yeah.
Lars, kan du ta disken?
So basically what I'm going to do here now is first the pushback processing. I will not show you that. That was Agnar did yesterday. And the VS dual processor, which also mosaics and merge Veneer and sphere cubes. So I will not, I will show the videos on the Svalbard data instead. Right. So yeah, let's see if there's anything else here I need to show from this video. This is the pushback processing, putting in the level arm as Agnar showed yesterday. Yeah, for this system here, it's you have a reference to IMU, reference to primary GNSS, and you also have the system is mounted internally, right, in the UAV payload, so it's not mounted with the correct coordinate system, so there is a rotation of the coordinate systems as well. And here you can actually, once you have found the Boresight angles, you can actually input those here, so that the data comes out. You don't have to add the Boresight file in parts actually. Yeah, and in process, you can see here the accuracy I mentioned. We have a single IMU, so we're getting around 9 to 10 centimeters or 9.5 centimeters. So here this is the plot of the actual events. You can see those on the performance, so you can see what it is during your flight. And here's the roll, and yeah. And for the this is two systems, right? So there's two reference points. So actually, when you're flying a gimbal, the reference point has to be the rotational center of the gimbal, and then you measure reference to output level arm, and the output level arm is the Veneer and the sphere camera. So you have to export separate files for Veneer and sphere. Yeah, and Hyperspex nav. This is, I'm showing this quickly afterwards as well. This is what was resampling, right? The events to the mid exposure of each frame of your system and actually resampling the INS data. And all these softwares, of course, comes in console, like Linux versions and console versions, so we can run it in batch. Yeah, and then I think we can go to Boresight. Yeah, now we are starting with parts. So let's move on. So just a reminder from yesterday as well. This is the processing flowchart for Airborne and UAV data when using Anaplanix. Again, Hyperspex Air acquiring raw data. Hyperspex RAD is using the binary header where all the calibration information is stored to calibrate the image to add sensor radiance. Pushback is processing the INS data, GPS and IMU to a 200 Hz INS file and an event file. And then together with the log file from Hyperspex Air, Hyperspex nav can then resample to mid exposure of every frame. And then you get one text file for each Hyperspex image with the frame number, XYZ roll pitch heading, and GPS time. So to do georeferencing in parts, you need that file. You need the sensor model, which is the geometric characterization from the lab that you get from us. You need an elevation or a surface model, and you need the Boresight file. Yeah, so what we're going to do now is actually, we have everything else here now. We are just missing the Boresight file. So that's what we're going to show now, how to do that. So just a quick yeah, run through on each of the steps before we reach parts is add sensor radiance calibration is converting from raw to add sensor radiance, and that's the traceable calibration, right? And this is an example of an older version of the GUI of Hyperspex RAD, right? You just select the files, you select the output format. For example, if you're running parts, BSQ is the file format it supports. So you have to convert to that, and of course you most often at least you convert to 32-bit float. You can convert to 16-bit, then it will be half the size, but you run the risk of losing some dynamic range if you are forcing it to fit into a 16-bit format. And you can do software binning in spectral direction and in a cross-stack direction. In the newest version, you can also do a long track direction, of course. Yeah, these are the 4 flight lines we are going to process today. This has is yeah, a little bit north of the or south of the runway in Longyearbyen. It's Adventsdal. Yeah, at least yeah. So that these are after radiance or radiometric calibration, and as I mentioned yesterday, you can see there are some striping here which I don't like. You typically see it over water when it's a lot of blue light.
Trond.
Yeah.
Can I just add that the data here, it's the data for Janne. So it's the SIOS project number 6, if I remember correctly.
Yeah.
Yes, that is.
Good, and I think the file that Fredrik Agnar is working on also for the demo or the hands-on with Envy is this one, the first one here. We're going to show some applications after lunch. Yeah, that I mentioned a few times now. Pushback is used, and if you use other solutions, as I said, the hyperspectral systems are typically can use any navigation system, right? And yeah, some RMR solutions and Novatel solutions have real-time outputs, which is the main output. And others you have software like Inertial Explorer and other software can be processing your INS data for you.
Trond.
Yeah.
Did you say that the previous lines were not corrected?
No, they are corrected, but it's unrectified. But I'm showing here a very the blue band is at 430, I think. So and you can see this is also BRDF. The white the blue haze on the side here that you see in the image is a BRDF effect.
Yeah, but you can just illustrate on the airstrip that it's not rectified. I think you have to look carefully to see that the lines are not straight. So this is before the rectification.
Yeah, I'm showing that. Yeah, I will show that in the video next, how it looks rectified and unrectified. The same lines. Yeah, Hyperspectral nav again. Does the resampling. Yeah, as an example of the GUI. Here you can select the division factor, right? As I mentioned, you can be used with any navigation system. There are some navigation system, for example, from IGI that only handles 2 Hertz on the event. So then you have to just divide it down by a bigger value so that you never go above 2 Hertz, right? Then you add the log file from the files, from the flights you have done. You add the event file from Postback or any other software. You add the IMU data, and then basically you are generating the text files. You can also here add the Boresight offsets if you have already found them. So again, just a reminder what is needed to get high performance. Of course, you need an INS system that has a high performance. We have actually, I will not mention that now, but we have had some customers buying extremely cheap INS solutions, like a couple of €1,000 from Xsense and suppliers like that. Of course, it will work. The image will still look okay, rectified, but it will be very bad when you're trying to the geofencing accuracy will be bad, and when you're trying to overlap it. But we have actually made a procedure to, it's time consuming, but to actually correct, let's say you're flying 10 parallel flight lines with a very bad IMU, we still have a procedure so you can correct all this so the mosaic looks okay. But it's a manual procedure where you are boresighting one flight line to the other and so on. Yeah, so you need a good INS, good GPS antenna, dual frequency with L-band if you need the online correction, timing accuracy, alignment. You need to do that. For Airborne, you fly an 8. For UAV or copter solutions, you fly straight and fast and stop fast. You need a very good Boresight calibration, high resolution elevation model, or elevation model that is similar in resolution to where your pixel size. Or if it's of course very flat in that area, you could live with a worse resolution elevation model. Gimbal, if you use a gimbal, either with an encoder or dual IMU for dynamic level arm compensation, and you need of course a camera that has a mechanical or optomechanical stability if you change pressure, if you change temperature, and you need the accurate sensor model as described yesterday. So since it's a push broom scanner, we need longitude, latitude, altitude, roll, pitch, heading for every scan line. And actually, if you used another architecture here, if you didn't use push broom, I didn't go through a lot of other architectures, but let's say you use whisk broom where you have to, for example, reconstruct the spectra based on the navigation system. So then you really need a high-end system, right? Because if you then have a navigation system that have an accuracy of half a pixel, that will actually introduce then in the co-registration 50% keystone or spatial misregistration in your data, just because you have a poor INS solution. So for example, you have some systems, for example, teleops systems for mid-wave and long wave. We are partnering with them for that wavelength area. Just their airborne mount costs €600,000 because they have to looking straight at the same pixels basically when they acquire all the wavelength. So it's yeah, it's another way of doing it. That's why I really like the push broom architecture. Boresight calibration, yeah. So when you have done this, we can do direct referencing without any points on the ground. If you have a dual system with Veneer and Sphere, what we do, we first boresight the Veneer, the Sphere camera to the Veneer camera. This is to ensure a good co-registration between those two sensors, no matter what kind of INS solution you have or what kind of elevation model you have. And then we do the Veneer to Earth, basically, boresight. So now we don't have a Sphere camera, so we only do Veneer to Earth boresight. So Veneer to the IMU coordinate system. Yeah, so we are finding the rotational offsets in roll pitch and heading between the coordinate system of the Veneer and the IMU. Yeah, and now I will jump to this video showing the process, how it's done in parts.
Let's start now with a Boresight calibration. Like Agnar showed yesterday, he showed how to process the navigation data. And now I'm assuming that now we have a file here, text file containing X, Y, Z, roll pitch heading for each frame in the high-space image. This X, Y, Z roll pitch heading is actually resampled to the mid-exposure of every frame. That's very important. So I'm going to show you one out of several Boresight possibilities in parts. This is the GUI version of parts, right? You can do all this in batch, of course. I will show you quickly some options for that later on. We will start. So I will show you then the different kind of Boresight calibration you can do in parts. You have some function here under control. You can basically collect GCPs manually from orthophoto and do Boresight calibration. You can do output GCP detection, so it finds the GCPs from you, and there it will use an orthophoto and a high-space image, and it will try to detect the same GCPs in both. So it's important then to use the same RGB bands as or the normal RGB bands, and also to try to resample the hyperspectral image to the same pixel size as the orthophoto. That makes it easier. Then you have crossed Boresight, which is the one we at Hyperspace are using the most reliable one, I would say now. Here, so basically when we do a Boresight, we fly 4 flight lines. We fly across over an area with a lot of GCPs that doesn't have to be known. And we fly both flight lines in both directions. Then that means 4 flight lines. And you have to have an elevation model of the area you're flying so that you get the set value from that one. That is the most accurate because then you are selecting the tie points basically between the two crossed high-space images. So you're not selecting a ground control point because you don't have the position of it. You're only selecting the tie points between two images, and with the elevation, it can still calculate the offset mismatch for those tie points to match. And then you have the automatic Boresight, which is doing a cross Boresighting, but automatically detecting the GCPs. So yeah, what I will show now for one cross is the manual cross Boresight, not the automatic one. So let's go there. So before you do this, right, cross Boresight, you have to have a geo-referenced image of your 2 flight lines that you're going to run in the first cross. So to do that, I put the raw data here, or the unrectified data here. So let's just open it in NME so we can see it. So I'm over TeamViewer now, so the bit resolution of the colors will not be representative of the actual image, but yeah, you just know that. So Boresight. Yeah, so here are the files, so I can open both flight lines. This is over the airfield in Norrabin. There, there. this is one image and the other flown in different directions. So you can see that this is not a rectified or Geo-Referenced image or rectified image. So then we will start with the georeferencing of those two without any Boresight. So then we are just georeferencing them in the coordinate system of the INS, not with the correct Boresight rotation. Yeah. So this Boresight only has to be done once for each installation. Once you take out the camera and put it back relative to the IMU, you need to redo it. But if you keep the installation stable, there should be no need to redo the Boresight. Okay, Hyperspectral Directory Processor. That's a special function that processes all the data in one folder. So let me just show you here. I'll just reset the status in case I used it already, but I will just show you the flight path once before I do the directory processor. Boresight. Let's just go for number one. And then I select the INS data. This is not part, this is the manual way of rectifying one-on-one flight line. I will not do that now. There. And then the sensor model file, which is the what I described yesterday in the second session, is the pointing angle of each pixel. And since Agnar have installed the camera in the opposite way than the normal, it's a rotated sensor model. And then I import the data. Here it's also important to select which datum you're using here on protection. So it's using VJ64 UTM zone 33 in this one. So you can now plot the image area here, and you will see the flight path. Not with a loaded dem yet, but we don't need to do that now. I will do the directory processor so it goes faster. So then it's processor batch Hyperspectral directory processor. I select the directory again, Boresight. Okay. It didn't find the INS files. Let's see. Seems that I added one too many. So I will remove the ones that are not needed. So basically, it's looking to find matching files, right? So here is the text file is the INS files, and the IMG files is the image files. So it was not now complaining that it didn't find the matching ones. And that's actually also a case. It needs a Boresight file. So I did some tests here already. So I have a dummy one with just zero parameters. Okay. The Boresight is with no. Okay, because it's looking for the name Boresight, right? In the name, and it's looking for the file, the same file name there in the beginning. So
just this GCS file, that's a status file from Patch, where the Boresight offsets are stored. So the dummy one here just has 000, but the directory processor needs a file to include, or it complains.
Let's start now with a Boresight calibration. Like Agnar showed yesterday, he showed how to process the navigation data. And now I'm assuming that now we have a file here, text file containing
start all over.
Yesterday in the second session, it didn't find. I have a okay, the same file name. So it finds everything. It finds the Boresight files. It finds the sensor model file. It selects the area you want to rectify, but it doesn't find the DSM file. So here I'm using the DSM which was generated based on the Phase 1 camera. This is in EGM 2008 Geo-Read height reference. Come back to that. Okay. Yeah. For the resolution here, I'll take guess range. There, found load will use more memory. Okay, that's okay. We are used to using memory. So let's not do mosaic now. There's no need to do that when we don't have the correct Boresight. Pixel field distance, I usually put that to 10. That's basically if you're flying.
I think you should pause. And you were a bit quick there. The DSM you're using is generated using the Phase 1 images.
Yeah.
Yeah, in Pix4D.
In Pix4D, yeah. And what resolution does that have again? I don't remember.
Yeah, it has 9 centimeter ground resolution.
Yeah. So it's a very good DSM to use for a Boresight here. But I guess we're coming back to that as well. For the area where we are processing afterwards, we only have the 5 meter resolution, right?
Yes.
Yeah. Yeah, so it's a very good combination, right, to fly the Phase 1 together with the Hyperspecs always, because then you can actually generate in Pix4D or Agisoft a surface model based on that.
Pitching and rolling a lot, you can get your footprint on ground can be quite stretched relative to the pixel level if you're not oversampling a lot. And then this will be, let's say you are moving 5 times faster than the actual frame rate. Then if you have a pixel field distance of 3, you will basically the georeferencing part will not look for any pixel longer than 3 pixels away. So you'll get dark pixels in your image. I will force the processes of all scenes. Great, then it will generate some JPEGs. Then I will process it. I'll put this to 0.5 meter, I think it's okay. And then process directory. When I press this now, it's just going to be running, and then we can start. When this is done, we can start the actual Boresight. So for example, here you could actually make a directory with 100 flight lines, right? And it will do everything automatically. But just keep in mind that you also need space for the Geo-Referenced image. So you have to make sure that on your hard drive, you have space for a Geo-Referenced huge image in the hard drive. While this is running, I can show you some other things here, right? So part is what we use as standard. There are other solutions out there. There are many people make their own. You have Envy have something. So you have many different options. We use Parch. Parch is a small company in Switzerland, but they're very good. They have quality in the final product is their main goal or main focus. You see, for example, here you can, as a quality control, you can look at, like I mentioned before, the pixel size. I will not do that now while processing, but you can look at your standard deviation of your along and across that pixel size. Then you can see how much turbulence it was, how much vibration, for example. And the data loss analysis is basically that. You will look at how many percentage of your image is undersampled, for example. So yeah, it's important. Quality control measures. Processor, here you have different ways of processing manually, right? The only batch processor here is the one that, of course, is the easiest to use. You also have a dual processor, high-spec dual processor, which can actually merge Veneer and sphere data into one common queue, which is in many cases what you want. Yeah. Then let's wait for the processing of the flight lines or georeferencing of the flight line without Boresight to finish. So Now when I process it now, actually, I use all the bands, right? Or it's small, usually we have more than 20 RGB bands.
We'll
So
jump
at
to-
the beginning of a campaign, you can use that to do the Boresight, because you don't care so much about your signal to noise ratio in your Boresight.
Yeah,
And that's also important to know, for example, because typically you would not fly in cloudy weather with the speed sensor, but you can use the cloudy days, right? If you're in the beginning of a campaign, you can use that to do the Boresight, because you don't care so much about your signal to noise ratio in your Boresight images. That's just to carry what you need to fly, right? So that's just to find the offsets. So yeah, the first day is always, after installation, is always Boresight, and that can be done in almost any weather. I would avoid heavy rain, but except for that, you can fly a Boresight. Okay, now it's the processing is finished. So let's then try to just open one of the files. Press done here in Envy, just to see how the rectified one looks. Yeah, so those are now 6.5 gigs. So this is number one. Let's select an area. Of course, Envy enhances it based on the totally test in the image. So sometimes the enhancement is not ideal. But now you can see the runway is straight, and yeah, looks a lot better. Let's open the other. Yeah, you have that. Only 6 out 30 bands now, because I've binned it 6 times, right? Yeah. Okay, let's go to the Boresight.
This is for the Boresight calibration, right? You, as I said, you don't care about the number of bands, the signal to noise ratio. So just to reduce space, I just put spectral binning to 6 when I process it in Hyperspectral Rad, because then the number of bands or the file size gets smaller and the Boresight goes faster. Of course, you could also select just to rectify RGB bands here, not all 30 bands.
Maybe Trond, you just to repeat that, for most people, this image now, it looks perfect. But to get the absolute georeferencing correct, the Boresight is necessary.
Yeah, so now it's processed without any offsets, right? So it's in the IMU coordinate system, and if you try to overlap 2 flight lines, you will probably have a 5-meter error, I think, with the offsets we have now. So yeah.
When you do this properly, right, you should select a lot of points. 30 to 50. Remember that you have, when you select 1 point, I would say that you have a selection accuracy of maybe half a pixel to 1 pixel. And then the total error is reduced by the square root of the number of GCPs or type points you're selecting. So the more you select, the better the offset will be. So now it's already loaded input file number 3 here. It's the wrong one. You should here load the actual Geo-Referenced image. So, for example, this one. Let's use 3 as input file. It actually used the map file for 1, so then I guess we can do the same. Let's then use 1. Then 1, it doesn't matter which one you select as the reference and which is the input file. But then we select 1 as input file. Yeah, 1 input, 1 is map file. And then you select the cross-referenced one. That's number 3, which is this one. And the cross-reference status file, it's this one. Okay. When I do this, I work on 2 screens. It's a lot easier, but of course it's worth to make a video when you have 2 screens. So I will try to fit it now in 1 screen here. So you show first the input file. Just select 3 bands you want to visualize. Select. Yeah. complaining that I'm using a lot of memory. Here. And then you show the reference file. Again, complaining.
So on this one, when I did the directory processor, I forgot to press guess range, because then it calculates a dimension that just fits the line. Here you can see there's a lot of dark pixel around, and all the dark pixel, they take up the bytes right in the file. So these files could have been a lot smaller if I did that previously.
Those are now the two flight lines. As I said, when I did the rectification of those, I use nearest neighbor resampling. That gives you the coarsest geometry in the image. It gives you pure spectra, which is extremely important, right? Because we are most interested here in the spectral information and the image looking good. You can select bilinear interpolation, for example. The image would look smoother, nicer to look at, but the spectral information has been resampled with the neighboring pixels, basically adding distortions to the image, like I mentioned yesterday. So I'll not select too many images today, or ground control points or tripods today, but let's select a few. It's always a good idea to enhance it so you can see the markings on the runway. I usually like to fly over runways because you have you have a lot of type points, easy to select or easy to find type points. Let's scale the zoom instead to medium, then it gets darker and the bright parts light up. Okay, and then we do the same here. So we don't have to do it on both. We can just jump to the current position. So this was the end of an arrow on the runway. So I can select the end of the arrow there. I can push this position and I can get it here. So now it's supposed to jump to the same position. I will just move here so I can enhance it similarly. I forgot the whole image again. Let's do only the zoom. So now the arrow you will have between push and get here will be the arrow introduced by the Boresight. So here you can see we are using here a different resolution than the actual one on the ground. As you're seeing, it's undersampled, but you can still select the end of the arrow here. So selecting the correct pixel output pixel size is extremely important. You can see probably here you flew slower than you did here. So probably there is a strong headwind and tailwind. Yeah, but let's push this position as well, and then you add the point here. So now 1 point is added. So let's move to the next. Here you have a yellow line crossing a white line. That's an easy point to find in both images, or should be at least. Push, get, yeah. Push, get. Then let's just move down. So as I said, I usually go down and select a lot of points in the runway. Let's at least try to select them now. Let's do this one. Corner of one of the large markings. So it's this corner here. Push, get. Zoom a little bit out. It's a bit easier to see where we are. Okay. Let's do the end of this one. So I use the mouse to press approximately, and then I use the arrows to find the
exact position. Of course, now I'm on our team viewer, so it's lagging a bit. Push. It's important to select good TCPs here. If you are in doubt, then just don't use it. Yeah, taking my own advice, I will not use this. Here. Push. There. So now we have 5 points, or 4 points actually, because the first one was already there. There's an empty one there when you start, so that also counts here. But get the position. Again, I will not use that. Push, get.
So this can be a bit boring when you do this with 50 points, but it's really necessary. So
Push.
when we fly UAV, we put out
So,
this.
as I said, you do this once for your installation, and then you can do direct referencing with those offset until you change the installation. If you're, of course, if you have a stable installation. So stable means that the GPS antenna and the camera and the IMU is mounted rigidly relative to each other. You do have installations, of course, with, for example, stabilized platform, where you have movement of the camera relative and IMU relative to the GPS antenna. But then you need to take that into consideration in the post-processing of the navigation data, which Agnar talked about yesterday. For drone systems, you actually have, as I also mentioned yesterday, possibility to correct for that real time by having dual IMU. Then it will correct for the dynamic layer run in the post-processing step. Okay, let's try to move a little bit faster here down the runway. Yeah, I have quite a few points now. So as I said, in a normal Boresight, I will do this many points, 30 to 50, but I will not do that now. Because on the data we are processing now, the limiting factor will not be the Boresight actually. The limiting factor here will be the elevation model. The elevation model for the area where we are flying is 5 meter accuracy, so it's a bit coarse. But the biggest problem is actually it uses a geoid for height reference. That is not one of the typical ones. It's a custom one for Svalbard, which basically we haven't looked into the differences between the geoids. So there's a few meter difference between those. That will cause a shift between in the overlapping region. But yeah, that's why it's extremely important, right, to have full control of the height reference, in addition, of course, to the projection. Push. Now we have 10 points. Let's just continue to the end of the runway here. Push. Yeah. Here's the And then the same here in the center here. Then we take one last one. Yeah, this corner here. Push. Get. Okay, now we have 14 points. So then once you're done here, you have to do the selection what you're going to actually do a process here now. You have a selection to do or optimize for row and pitch, but also add heading. So heading, I will add here now. Usually heading is the worst to find, so that needs many points. So you should have more than 14 points to the heading, but I will still add it. You can also put if your flights, if you use parallel flight lines to the Boresight instead of crossed. Then I just press cross Boresighting, and it will spend some seconds or maybe a minute or two to do the processing. Yes, so now it can found the offsets here, which is minus 0.2 in row, 0.05 in pitch, and 0 in heading. So it's just the heading is quite aligned. That might also be that it's too few points. With the RMS error in meters, quite low relative to the pixel, was 0.5 meter, right? So it's very good. For this area here, as I said, here you can get the Boresight very good. Or the Boresight will be good, but because here you have the same byte reference. Here you use the EGM 2008, both for the navigation data and for the surface model made by the phase one. For the other area flying, it's in the Svalbard grid, so there will be an offset. So that's also, of course, something you can apply if you know the offset. So then you save the file, save status, and okay, we are not here. We are in Boresight, yeah, and I will save it as Boresight cross program 1 and 3. Okay, so now we have a Boresight file. The reason we fly 4 flight lines is that to check for consistency that you have the correct offset, we always recommend to fly or to process all 4 combinations, like 1, 3, and 2, 4, and 4, 1, and 3, 2. Because that then you will get the 4 different offset or 4 different combination of flight direction in the cross, and those should match the offsets. If they don't match, then you have a problem with one of your inputs, right? Typically, as I mentioned, height reference using ellipsoid instead of geoid or different geoids is a very normal error. A normal error is to use different datums on the elevation model and on the Hyperspectral data. Yeah, you can have a level arm, which Agnar mentioned yesterday. It's very important to input the correct level arm, right? So let's say you have 0.5 meter error in the level arm, and you're doing a turn. Then actually you are introducing a 1 meter error in your data. So all these things is extremely important to do if you want very high accuracy directory referencing output. Okay, then I will stop here and I will start a new video where we are doing directory referencing on 4 flight lines that is flown over an area just south of this area here.
Yeah, so now we are, it's a lot shorter video about the directory referencing once you have the Boresight file.
Okay, let's start with the data referencing. Okay, let's first check out this elevation model we are using. So this is the elevation model. It's 5-meter resolution, so this is quite large scale. Yeah, let's open it in Envy and have a look at how it looks. So when you're doing something else, we always reset session. So let's start now. I will import them. Like this. Then I will import one of the flight line.
Just of course, this is not something you have to remember every step I'm going through here now, right? It's if you ever work on this part of rectifying data and stuff, of course they are in the instructional videos and quick start manuals, step-by-step manuals to do this. So it's just this is for you to understand the procedure. Is the main objective here.
I want to I'm not doing the directory processing now. I'm just gonna do an evaluation of the actual pixel size in the image before I process it. So I open number 2, line number 2, without knowing exactly what that is, but there. INS data, then I select the sensor model. So this is the process that where if you want to rectify one flight line, you would, that's the old way of doing it, where you open here, you import the data, successfully imported, and then it also converts that long to UTM zone 33, right, and so on. And now you will have an image area shown, and the red here is the surface model. So this is the flight path that you have been flying. And to do an evaluation now of the pixel size, you first have to do the main processor. So main processor is basically making a map file telling you the position of each pixel in your unrectified image in UTM coordinates. Yeah, so this takes a bit of time. Yeah, let's see how then, while we're waiting for this, just how this image number 2 looks. Here. Yeah, so that's water and seabed. Let's try to just mix around on the balance here.
If you haven't worked with Envy before, this is going to be shown later in the next session as well, right? How to play around.
This is the one we're just going to rectify now to have a look on pixel size and the what we are selecting as an output pixel size, right, for our system.
Now I'm just selecting different RGB bands to show false color RGB in Envy.
Okay.
I think I can.
So this is the INS files here. That's what it looks like. We frame. We have good for you have one for each of the images. Sure.
I will just jump to this being done.
Yeah, then it's been done. This takes a while to do this geometry map decoding. So
basically what I'm doing here is I'm just trying to let parts find the pixel size in the final grid. That's the kind of the idea why I run this process before directory. Of course, you can do this based on your flight planning. You know you flew this height, you know you flew this approximately this speed and so on. But this way, you know, this is based on actually one image, and you can see what kind of pixel size both across and along track that part is reporting.
Great, and it's finished. Now we can look at analysis for 3 seconds. Now we can look at the what I wanted to look at. For
It's
example,
getting blurred again. Your screen is
display the
getting
flight
blurred.
path on the.
What?
Your screen is blurred again. Yes, now it's fine.
Okay, might be. I see it's working on something in the background here.
It's fine for me on my side.
Okay.
Okay.
Let's start with the diagram.
Okay, now it's. There.
Okay, great. Then it's finished. Now we can look at the analysis for 3 seconds. Now we can look at the what I wanted to look at. For example, you can look at the display the flight path on the elevation model here. Let's do that first. So this is where this flight was taken. Let's look at the QC or quality control plot. So if you go to RGM pixel size here, it will generate what's your along track pixel size and what's your across track pixel size. So yeah, so here we have 1 meter across track and 1.4 meter along track. So that might have been yeah. So in this one, I actually did 3 times along track binning. So I see now that I should have only done 2. But we will stick to the 3 times since I've done all the processing already with that.
Yeah, so basically me and Agnar discussed before I got the data, and I decided to bin this the radiometric file 3 times along track because he is oversampling with a factor 3, I believe. But looking here now and the speed that has been flown and the altitude, the average oversampling factor was closer to 2. So I should have only done 2 times binning, but yeah, we don't change that now, of course.
But we will select 1 meter resolution on the output. And you can see this is the standard deviation here. It's about 10% actually of a pixel, which is very good. That means it's not much vibration and not much movement, roll and pitching during the exposure of 1 frame. So the motion blur is not too bad. Okay, now let's move directly to the directory processor. There's batch here and high-speed directory processor. Yeah. And here you select the input directory, demo mosaic. Then it allows you finds the surface model, it finds the Boresight file, finds the sensor model file, finds the area it wants to rectify, suggests a pixel size 1 meter. And here is the resampling method. So if you want the image to look the nicest, it's the bilinear interpolation. It gives you the best geometry but changed radiometry. And we don't want that. We want pure radiometry. So nothing has changed in the pixel. That will contain or keep the spectral fidelity that I talked a lot about yesterday. But it will give you poor geometry or not so good looking image. But that's a second priority here. If you're generating a very nice image for an article or whatever, you could just process the RGB band, for example, in bilinear interpolation. Pixel field distance, that's on drone system where it's pitching and rolling a lot. I usually use 10. This is basically when it's doing the georeferencing or the rectification to the new grid that you now have selected. This is the new grid right here. It will look for a pixel within 3 pixels away. So if it doesn't find a pixel within 3 pixels, that can be, let's say your aircraft pitches a lot, for example, then the field of view on ground can move very fast, and you might not have a center coordinate of a pixel closer than 3 pixels. Then you will get a dark pixel. That's why I select them here, not even dark pixels, but As you saw, this image was very nice. It was flown stably with very low standard deviation, so 3 would have been okay to use here as well. For processing all scenes, then you get a file for all scenes. You select this, you get an RGB preview of each line, and you have a mosaic here. And then basically you just press process directory and it will run. For this one here, it's generating 4 files, each of them probably 20 gigs, and then a final file at the end. So it will probably take half an hour to process this. But let's start, and then we will forward the video. Okay, now let's move directly to the directory processor.
There. Sorry.
Okay, then the directory processor is done.
So now I skipped half an hour ahead, and yeah.
So now, basically, just by selecting this, it has processed the Geo-Referenced and mosaic 4 flight lines based on the Boresight that we just did. So let's try to open the file here. So now just for your information, right, when you see here now on the file sizes. So the file size, if I go to the raw data or the calibrated data, has gone from around 8 to 9 gigabytes per line, and then to the output to 70.6 gigabytes on the final processed image now. So here we have the processed data. It's a full mosaic. And as I said, the height model is not 100% correct. So I'm suspecting that mosaicing will not be perfect. Let's just evaluate that on the road here. Let's see. Yeah, so there's a small, let's see, it's number 4. Yeah, so you can see it's not 100% match here in the raw. But that's again due to the height. So yeah, this is the false color RGB. This is the default RGB bands. If I put the set profile here now, you can see which band is selected as red, green, and blue. So I can move around on that to play around with which RGB is shown. But this is a very simple way to process your images. Takes very little time. In the next session, Federica now will show you a bit about how to do processing by like application-specific processing on this in Envy. Yeah, so now I'm going to also start processing another job, another 6 flight lines in this directory processor. So thank you very much.
Okay, just for if you are having a processing computer working on this, a limiting factor could be the rate of storage, right? So you should definitely have huge SSD drives when you're doing, like your working directory when you're doing processing. If you use conventional drives, it will slow down the speed a lot on the processing. Yeah, just then we are done with the videos. Just show you quickly the overview of what was generated, just the JPEG preview of each flight line that is automatically generated if you press that button in the directory processor. So it's processing line 1 to 4. This is line 1, line 2, line 3, line 4. With the Boresight offsets that we generated earlier, and then the final mosaic. So it's just I have played around on the final mosaic with the false color bands used. That's why it looks different, right? In relative to the others. These are automatically generated, those 4, while this one I generated in Envy. Yeah.